Hello everyone, I'm Jacob Czekareski and I'll present our paper titled Wi-Fi-VLC Dual Connectivity Streaming System for 6 Degrees of Freedom Multi-User Virtual Reality. This is a joint work with Maximization and we gratefully acknowledge the support of our sponsors. Our indoor VR arena system comprises an edge server that streams 6 DOF content to mobile VR users using two wireless technologies, visible light communication or VLC and Wi-Fi. We divide the spatial area of our arena into cells, and there is a ceiling-mounted LED transmitter above each cell. The server is linked to the LEDs and the Wi-Fi access points using fiber optic links and controls them. There are two IR base stations that track the user's 6 degrees of freedom coordinates, and there is a baseline and enhancement content layers streamed to each user over parallel Wi-Fi VLC links, and the users wear dual connectivity headsets. Our main contribution in this context are: we carry out edge adaptation of the present omnidirectional viewpoint of a user in the 6 DOF arena using scalable tiling to construct a panoramic baseline content layer and a Viewport-specific enhancement content layer. We then explore synergistic Wi-Fi VLC dual connectivity streaming of the two content layers, and we carry out formal ray distortion analysis and optimization of the server's actions and formulate a corresponding low complexity solution enabled by the use of scalable tiling. To address the fragility of mobile VLC links to transmitter-receiver misalignment, we investigate dynamic VLC transmitter steering and assignment via graph bottleneck matching and formulate a lower complexity polynomial time solution to solve the problem of interest. We also contribute the first public 6 DOF VR navigation dataset, and we demonstrate strong viewport quality and application reliability gains of a traditional state-of-the-art and Li-Fi, that is VLC-only approaches. The motivation for our work is the virtual reality is an emerging technology with prospectively broad societal impact. However, up to now it has been limited mostly to gaming, entertainment, cable operation and low-fidelity graphics. And that is because it imposes challenging requirements in the form of ultra-high data rate and ultra-low latency that cannot be met by present or upcoming traditional networks. Moreover, existing 360 video practices are quite underperforming as they map traditional video approaches to this new context. And similarly, the mobile VR experience is particularly poor due to the even more limited bandwidth and computing resources existing in such environments. However, untethered high-fidelity VR applications can have the high societal impact, advancing quality of life, the global economy, energy conservation, and even making impact on the COVID pandemic at present. There are several new technologies that we leverage in our work. VLC can transmit data at very high rate. However, VLC links are fragile due to the directed narrow beam nature, and we address this challenge as part of our work. We also integrate edge-based operation that helps bring the data and computing closest to the user to minimize the interactive latency. And finally, we integrate scalable 360-degree tiling to enable viewport adaptation and leveraging ray distortion trade-offs associated with the content. Recently, there have been several studies that explore tiling-based viewport adaptive streaming for efficient utilization of network resources. Still, they are restricted by the fundamental limitations of traditional wireless technologies and server-client architectures they use. This is in stark contrast with the expectations for next-generation high-quality immersion, which would comprise 360 panoramas of 12K spatial resolution and 120 FPS frame rates, as established by MPEG. Moreover, we integrate in our work our recent advances in VLC-enabled headset design. Here's an outline for the rest of the talk. We first present our major system models and components. We then formulate the problem of viewport quality maximization in our arena that we investigate. This is then followed by experimental analysis, and we conclude at the end. We model the 6 degrees of freedom content as a collection of omnidirectional or 360-degree viewpoints across the area of the arena that the users can select to navigate as they move around. We then use scalable 360-degree tiling to represent each such 360 viewpoint into multiple signal layers, as illustrated here at the bottom. Concretely, we compress each GOP tile into multiple embedded layers of increasing fidelity. The baseline enhancement VR content sent to user U are then constructed by combining multiple such tiling layers. We benefit in our work from our recent advances that enable us to accurately capture the viewport quality delivered to user U as a function of the assigned Wi-Fi and VLC downlink data rates to this user. We know that for mathematical convenience, we work with the expression for the viewport distortion here, with no loss in information due to the one-to-one mapping between quality and distortion. Mobile VLC links can be sensitive to misalignment that can induce transient connectivity loss if they are used exclusively. Therefore, we pursue the synergistic integration with Wi-Fi and the design of the two scalable content layers sent to a user. Concretely, the baseline content layer comprises the full 360 panorama for the user and is sent to a Wi-Fi to enable application reliability. The viewport-specific enhancement content layer is sent over the respective VLC link to enable high-quality immersion. Normally, the two content layers are received and can produce a high-quality viewport for the user by their synergistic integration as illustrated here. On the other hand, if the directed VLC link experiences a transient loss, or there is a mismatch between the transmitted viewport-specific content and the actual user viewport due to rapid head movements, the user can still reconstruct his viewport solely using the baseline content layer, thereby avoiding any prospective application downtime. We equip the VR user headsets with dual Wi-Fi VLC receivers. The VLC receiver comprises a placement of multiple photodiode layers along the upper hemisphere of a headset for a robust VLC link, and it is illustrated at the bottom of this slide. We use an optimization-based angle diversity approach to carry out this design, benefiting from our recent related advances, and this enables robustness to VR head movements. Now, we are interested to maximize the delivered viewport quality across all users in the VR arena, as formally described here, where the optimization variables of interest are the assigned Wi-Fi and VLC downlink data rates to every user U in the system. For fairness, we consider that the transmission capacities of the Wi-Fi access point and every VLC transmitter T are uniformly shared across the set of respective users they serve. This can lead to simpler, parallel convex optimization across every user transmitter pair. Enabled by the scalable layer nature of the content and the monotonic objective function du, we can further decompose each such parallel problem into two simpler sequential subproblems. Moreover, enabled by the scalable tiling of the present 360 viewpoint of user U, we can formulate a very lightweight solution to the two subproblems. It simultaneously solves the subproblems and constructs the baseline and enhancement content layers sent to this user. Effectively, we first find the first LB layers across all tiles in the 360 panorama that collectively do not exceed the Wi-Fi link capacity for the user. They will comprise the baseline content layer. We then find the subsequent LE layers only for the viewport tiles in the panorama that collectively do not exceed the VLC link capacity for the user. They will comprise the viewport-specific enhancement content layer. We refer you to the paper for more details. To account for the user mobility and maintain and optimize the fragile VLC connectivity, we explore dynamic VLC transmitter assignment and steering. We consider that the transmitters are mounted on mechanically steerable platforms to point them towards the users. The platforms facilitate the 6DoF user tracking information in their operation, and they comprise two servo motors that can control their vertical and horizontal rotation. As the users move around, periodic transmitter reassignment is carried out during a session for maximum performance. We illustrate the basic principles of the transmitter assignment in steering with the three illustrations shown here. In the one to the left, we indicate that on the beginning of a session, each user is assigned to the transmitter in the cell where the user resides at the start of the session. As a user moves from one cell to another, its assigned transmitter is tracking the user and basically redirects its beam towards the new location of the user. This is captured by the illustration in the middle. Finally, if it happens that two users are co-located in the same cell, their transmission beam will interfere with each other. Within this context, we are interested in exploring the transmitter assignment that will maximize the smallest received SNR across all users in the arena. Now, because received SNR is inversely proportional to the distance between a user and a transmitter, this is equivalent to solving the min-max problem shown at the bottom. Now, this problem is of combinatorial complexity, meaning it is NP complete. And to address this challenge, we formulate a lower complexity graph theoretic method, where we basically divide the users and the transmitters into two subsets, and we construct a weighted bipartite graph between the users and the transmitters, where the weight between each pair of nodes comprises to the distance between the respective user and transmitter, as illustrated here. Now, we can solve then this assignment as bottleneck matching on this graph, where we're interested in finding the maximum size vertex matching whose largest edge weight is as small as possible, as formally represented here. Now, in the graph, we formulate we formulate an efficient algorithmic solution using a Dulmich-Mendelssohn decomposition to solve the problem of interest. We also carry out VLC link channel modeling to support our analysis and evaluation. In particular, we characterize the LED lighting as a Lambertian radiation pattern. We then use maximal ratio combining to integrate the VLC signals transmitted from every transmitter in the arena and received at each photo detector of a VR headset. The expression here shows the received SNR at a user from transmitter T, where the received power of every VLC signal is weighted by a combining factor lambda. We refer you to the paper for more details. The VR arena setup that we used to collect 6DoF navigation data and carry out simulation experiments is shown in the picture in the lower left. There were 80 participants in the data collection, wearing the HTC Vive wireless headset and navigating the 6DoF content museum streamed from the server using the software SteamVR. The navigation data was collected using the OpenTrack software, and each navigation trace of a user comprises 30,000 tracking samples. In our simulation experiments, we set the VLC transmitter's beam width to 25 degrees and the half-angle field of view of the photo detectors on a headset to 1.5 of this quantity. We compressed each spatial 360 viewpoint in the content into scalable tiling at 12K spatial resolution and 120 frames per second. We assessed the delivered viewport quality by measuring its PSNR over time for every user in the arena. We compared the two state-of-the-art methods, Li-Fi, a cellular-based VLC system, and Dash, which uses the latest streaming standard and Wi-Fi in its operation. We first examined the temporal viewport quality for a user with 6 users co-present in the arena, while we also included a variant of our system that uses only VLC, that is a single link, to stream the content. We can see that the viewport quality varies over time for all 3 compared methods, due to transient VLC link drops or a mismatch between the delivered enhancement layer and the actual user viewport. Still, the observed viewport quality variation is much lower for our system, which considerably increases its quality of experience and reliability relative to proposed with no Wi-Fi and Li-Fi that experience an application downtime during such instances. On average, viewport quality gains of 5 dB and 7 dB and 3 times smaller standard deviation of viewport quality are enabled over the latter 2 methods, as seen from the 2 smaller inset graphs to the left. Finally, the user experienced 22% application downtime for proposed no Wi-Fi and Li-Fi compared to 0% downtime for our method, as shown in the inset graph to the right. These benefits merit the integrated dual-path streaming and scalable 360-degree rate allocation. Next, we examine the average viewport quality experienced by every user. The respective standard deviation is indicated on top of each bar. Our system enables a consistent 6.5 to 7 dB gain over Li-Fi across all users and 2.5 to 3 times smaller standard deviation. These advances will considerably enhance the user's quality of experience. We can further see that Dash enables poor viewport quality, only 39 dBs, as expected. On the other hand, our system delivers a high-quality viewport of 50.37 decibels for 6DoF VR content with 12K 120 frames per second, 360 viewpoints to notably advance the state-of-the-art. The performance gains of our system are enabled by its optimized dynamic user-to-transmitter assignment and narrower transmitter beam width, which help achieve consistent higher data rates, and our synergistic VLC Wi-Fi dual-path streaming and optimal 360-degree rate allocation. Finally, we examine the robustness of our system to its user load. We can see that for both methods, the average user viewport quality degrades as the number of users in the system is increased from 6 to 12 and 18, as expected. For Li-Fi, the likelihood of having multiple users in one cell during a session increases with the number of users, which will reduce the data rate per user. Similarly, the VLC interference experienced in our system increases with the user load, which will penalize the delivered viewport quality. Still, across all three cases, our system demonstrates consistent 6 to 7 dB viewport quality gains and more graceful degradation performance with the user load. In conclusion, we explored a future Wi-Fi-VLC dual-path 6 degrees of freedom multi-user VR streaming system that enables reliable, high-fidelity immersion. Key components and technical advances of our system are edge adaptation of the present 360-degree viewpoint of a user into two content layers using scalable tiling, synergistic Wi-Fi VLC dual connectivity streaming of the two content layers, formal rate distortion analysis and optimization of the server's actions, and dynamic VLC transmitter steering and assignment by graph bottleneck matching. We also contribute the first public 6.VR navigation dataset, and we demonstrate strong viewport quality and application reliability gains over traditional state-of-the-art and Li-Fi, that is VLC-only approaches. Thank you.